Good afternoon, all. My name's Tabitha Binding, and I'm Head of Education for Timber Development UK. Welcome to TD UK's webinar series on engineering with timber. This series aims to add to your engineering education so that as we transition to a bio-based economy, you have the tools and knowledge to include timber within the projects you work on, whether they're new build or retrofit. Webinar 5 is an introduction on designing with engineered timber products. Timber Development UK has been formed from the merger of two of the largest and longest established organisations in the supply chain, the Timber Trade Federation and the Timber Research and Development Association, which is obviously better known as TRADA. We're seeking to connect the supply chain, to lead best practice, and to accelerate towards a low carbon future. Our platform is Zoom meetings so that you can communicate with us and your peers. Please post any questions in the chat, which we will come to at the end of the presentation. And today's webinar will cover definitions, applications, and structural design principles of various engineered wood products, as well as good site practice, which should be followed during construction process, unless Kelly and Wojciech have completely changed it. So our speakers today are Kelly Harrison, Director of Whitby Wood, and who also sits on the board of TD UK, and Wojciech Plowas, Structural Timber Design Consultant and Lecturer at Edinburgh Napier University. So I'd like to hand over to you both to talk about design with engineered timber products.
Thank you, Tabitha. I will start sharing my screen now, if that's okay.
Yes, please.
Okay. Okay, so I guess I will start now. Welcome, everyone. My name is Wojciech.
Oh, wait,
yes?
Would you move your little bar to the top right?
Oh, yeah.
Is that okay? Thank you.
I'll discuss. There we go.
Perfect.
Thank you. So let's start again. My name is Wojciech Plowas. I'm a research consultant here at Napier University. My background is structural engineering, and for the last 8 years, I've been heavily involved in research and development of various mass timber systems and products, mainly using homegrown resource. And by means of introduction, just to put things in perspective, I prepared this very quick slide showing kind of backlog of our projects that we've carried out here at Napier, starting from 2009. That was obviously before I joined the team. I joined the team here at in 2015. Again, quite a lot of research projects done to date for many different types of funders. And that kind of led me to invitation to provide this presentation on mass timber systems. So today's presentation is split in 4 sections. I will start with introducing some engineered wood products, and I will hand over to Kelly. That will talk a little more about production and assembly side of things, and section 3 is about structure design. Some aspects. I mean, I've got limited time, so I will try to cover the most interesting things. And we're going to finish off with some challenges and barriers associated with mass timber construction. So, timber is a natural building material, which is its biggest advantage and disadvantage. I mean, it's a living thing, and the trees can only grow as tall and as wide. And because of that, the scope of applications is limited for sawn timber due to what I said, maximum cross sections, availability of species and different log sizes, and presence of naturally occurring defects. And because of these reasons, over the years, engineers and architects and like-minded people came up with very clever ways of combining smaller wood pieces, whether planks, chips, veneers, to form a larger, mostly structural elements, such as panels, sheets, and beams and columns, to increase the scope of application of timber. And this is basically a definition of engineering wood products. So large elements made of wood formed using planks, chips, veneers. And when you do that, you overcome many limitations of sawn timber. Engineered wood products can come in a variety of forms and shapes. Their size is limited only by the capacity of the factory or transportation. In production, the naturally occurring defects, such as knots, are often removed, and final product is more dimensionally stable due to the requirements of drying down the components of engineered wood products to the required moisture content, so it reacts properly with the adhesive or on the ways of fixing it together. So there are very many ways of grouping engineered wood products. So if you look at the literature, you will find many different ways of doing it. The way we adopted it here at Napier, and what I see quite often in the literature is this kind of split. So the family of engineered wood products, the first one, probably the most popular one, is the mass timber. So this is only the CLT, glue-laminated timber, laminated veneer lumber, double laminated timber. So the list can go on. Those are four most popular types of mass timber systems. This is where the planks of wood or boards are glued together in various orientation. I will talk a little more about that in the following slides. Another group of engineered wood products are wood-based panels. So those are the long, wide, but thin sheets of boards, often used for framing, packaging, flooring, and so on. So some common examples in this group include orientated strand board, better known as OSB, plywoods, particle board, chipboards. The third group of engineered wood products are structural assemblies. So in this case, the naming kind of varies slightly, but that's how I tend to say it. So this is where solid timber or engineered wood products are combined together in various ways to form a structural, efficient, load-bearing elements. Some common examples include thin web joists, metal web joists, or truss rafters. Another types of engineered wood products that did not make the list above, but they should be mentioned when we're talking about this topic, are modified wood. This is where the wood can be densified, acetylated, or thermally modified to increase its durability. And also there's a wood fiber insulation raising popularity in recent years. Now, in terms of application, so I've prepared a slide just to show you where the most common ways of using various engineered wood products, in this case timber frame construction. Starting from the roofs, so EWPs can be used as rafters. For example, thin web joists can be used as rafters, but most commonly there's actually truss rafters that are used for roofs. In terms of the sheathing or sarking, as we call it in Scotland, it's plywood or OSB. So this is to form this rigid panels or provide this diaphragm action to the roofs. So most commonly OSB or plywoods are used for these applications. In the areas where the high load-bearing capacity is required, like above openings, it's possible to use glue-laminated timber or laminated veneer lumber, as those mass timber products tend to be quite strong, and we can make them quite big, so they're suitable for these applications. Same with the trimmer joists. So if you're dealing with a multi-story building, you're dealing with increased stress. So the location of the increased stress where the other joists are landing, you might want to consider using some mass timber in this cases as well. Floorboards, again, this is where wood-based panels are most likely to be used in terms of, for example, chipboards, plywoods, or OSBs. Floor joists, most commonly engineered wood products used for these applications include thin web joists and wall studs. There are also ways of using thin web joists as a wall studs. This is actually a very efficient way of increasing the insulation of the wall So next few slides, I will talk a little more in detail about some of the most popular engineered wood products, starting with the CLT. So the cross-laminated timber, or CLT, is a structural mass timber or timber product with a minimum of 3 cross-bonded layers. So this is the main characteristic of this particular product. The layers are, the boards are cross-bonded together. Those layers comprise of structurally graded boards. So this is a requirement. All boards that go into CLT must be structurally graded. And in the production, boards are laid down in the press, and then the pressure is applied over the entire surface of the panel until the adhesive cures. Typically, cross-laminated timber consists of odd number of layers, which may be of different thicknesses, which gives you the flexibility of the overall section size. But those layers are generally arranged symmetrically about the middle layer. Applications. So CLT is commonly used due to its self-supporting capabilities. It can be used as a floor, roof, or wall slabs, or roof panels, floor panels. Very commonly, this construction technique, as you're going to see in the following slides, are used in multi-residential schools and sports halls. For every product I'm going to show you today, I also included this reference to a standard. So if you're keen to learn a little more about the requirements of each of the engineered wood products, you can refer to this product standard. So this quite specific set of information you can find there. Again, another one on the list is glue-laminated timber. So it's quite similar to cross-laminated timber, with the main difference is that the boards are arranged parallel to the main axis of the member. The boards must also be structurally graded. They're typically between 25 and 45 millimeters thick, but smaller laminations are also used when curved or vertical sections are required. So in terms of the structural capacity, it will be dictated by the overall section size and grade of timber used. So you can play with or specify different grades of timber that go in different layer, which again increases the scope of applications. Glue-lam is most commonly used for large structural elements, posts, beams, bridges, as well as heavy timber framing elements or curved shapes, as you can see on this picture here. LVL, or laminated veneer lumber, is manufactured from thin peeled veneers of softwood or hardwood. Those veneers are usually 3 millimeters thick. In terms of the grain runs parallel to the main axis of the member, although veneers may also run perpendicular to improve the dimensional stability of the member. So the panels of LVL are quite large when they come out from the factory, but then they are cut into smaller pieces to form a structural member with a very high strength and stiffness. And that kind of leads me to the applications. So LVL is very strong, comparing to the previous products I've described. So you could probably want to use the LVL in the applications where higher strength is required. Because it can resist much greater flexural or axial loads, or combination of both. It's suited for structural applications such as panels, beams, joists, and columns. Plywood, in principle, very similar to LVL, but it comes as a panel product, so it's wide, long, but thin. It's made from thin veneers peeled from the log. Veneers are bonded with a structural adhesive with a grain of adjacent layers, veneers usually orientated at the right angles. Applications, so plywood is, I'm sure all of you have seen plywood in some form or another, but in terms of structural applications, it's often used as a sheathing or sarking for the roofs. OSB, unlike plywood, it's made from strands or flakes that are bonded together with the synthetic resin to form like a panel, very thin but wide and long panel. interesting fact is that the OSB comprised of external and internal layers, and attention need to be paid to kind of direction of those flakes, because the external layer will have flakes or strands orientated in the long panel direction, and that will have a very this is very important from structure point of view. You should know which way the flakes running, because the properties of the OSB will be different in different directions. In terms of applications, very similar to plywood, very commonly used for wall sheathing or roof sarking. And the final product I will introduce today is the thin web joists. So those are the products that comprise of flanges made of solid wood or LVL, and the web made of plywood or OSB or particle board. So this is a very efficient way of using material. So this I section is very commonly used in structural engineering for a reason. So basically, in this case, flanges resist bending stresses because they go either in tension or compression. And as we know, timber is very good in this regard, was the web made of OSB or other panel products resisting shear stresses. As a result, we can obtain a structural member who's capable of carrying as much loading as solid timber joist of same section, whilst using much less material. So as name suggests, those engineered wood products are often used for floor joists or roof rafters. They can also form load-bearing studs or prefabricated cassette floors. Okay, that's in terms of the introduction. I will now hand over to Kelly to talk more about production and assembly of engineered wood products.
Yes, thank you. Thank you very much, Wojciech. Hopefully that is sharing now okay. Thanks, Tabitha, for letting me know. Hello, everybody. Yeah, so this is talking a little bit more about engineered timber today. And after that introduction from Wojciech, I think I just thought I'd introduce who I am a little bit. So I was part of the advisory committee and board of directors of TRADA, which now is Timber Development UK. Also been working with a collection of other organisations to sort of spread the word about mass timber in particular, but timber as well generally, and really sort of break down any barriers that there might be to using timber and building in a low carbon and sustainable way. And so today we're talking about engineered timber, and I'm going to sort of hone in a little bit just with some examples of mass timber production, just because I've got some nice photographs of some factory visits that I did not so long ago, and going to see an engineered timber factory really makes you understand how it goes together and how best you can design it. It's an off-site product. You should design it for manufacture as well as end use, and all of these things are super important, because there have been lots of buildings, and I'm absolutely guilty of this as an engineer, where we start off and we've probably done a design for a steel frame building or a concrete frame building, and we think, oh, let's make it timber. And so we do, and we use the same grid, and we use the same connections, we use the same number of beams. And then once it gets to the point of doing fabrication drawings, we realize you have to change everything. And then again, once it gets to site, there's more problems. And so you end up having to post fix things and adjust things when you're on site. And so really understanding how things are made in the factory is super important when designing from scratch, because if you can stick to the limitations of that, or not necessarily limitations, but or find opportunities in the limitations of that, then you can have a much better building at the end of it. And so for engineers and architects, it's super important to understand how it's made. So I'll just show you a few photos now of a factory visit I made about a year ago now to Rubna in Austria, and we saw there some glue-lam and some CLT being made. So this is a series of those lovely pieces of small pieces of sawn timber that Wojciech was just talking about that go into a glue-lam beam. I think these are about 40 millimeters thick each, which is kind of quite. I kind of like to have a starting point when I'm designing a glue-lam beam or column of the depth, in the direction of the lamellas to be a multiple of 40, because the sort of larger manufacturers of glue-lam tend to use those thicknesses, but you can have other thicknesses. So it's definitely worth speaking to them early on and seeing who might be supplying your glue-lam and what sizes then create the least wastage, because you're going to pay for the whole thing no matter what. They'll just cut it down. And also that means there's wastage in terms of embodied carbon as well as cost. So it's worth getting that right if you can. And then also trying to, generally we want to have widths of multiples of 20 millimeters as well. So you can see here just a bit of an overview of what the factory looked like, a few pieces before they've been glued together, laid out here, making some glue-lam beams. And the big thing about glue-lam and CLT, how it's made into long lengths. So you have your pieces that maybe they're about 5 or 6 meters long maximum, and that you get cut straight from the log. But then we want to probably make beams that are like anything up to 15, 20 meters long, maybe more realistically 6, 7 meters, or maybe 9 meters if we're doing something large. And the way we get those lengths of all the lamellas to connect together is by using a finger joint. There was some aggressive machinery that I saw that I think they used to do this. A picture on the left, and then basically this creates a super strong joint. And having done some testing of some glue-lam a few years ago now, I can confirm that this joint, once glued together, is extremely strong, because we tested a piece and applied the load right on the finger joint, and it actually split just next to the finger joint. So the finger joint was stronger than the timber next to it. So super strong, and gives us a nice stable material. Now you can see these pieces in their sort of 5 meter lengths here, about to get finger jointed, and on the right here they're being glued and pressed. Now this was an extremely long curved beam, so they're not normally created in such elaborate pressing, but it was rigged up especially for this sort of long curved beam that was going on, with various different, that was stepped at the ends as well. So you can see at the end there's oh sorry, gone too far. It's actually they've stepped the lamellas rather than making a whole piece and then cutting it later. So it's very materially efficient the way they've done this one. So that's being pressed with the glue between. And here that some of those beams are finished, and they're being checked by inspectors. Any small defects are being fixed, sanded back, and also here the connections are being applied. So quite often with glue-lam beams, your steel connecting parts will be made in the factory as well, and so you have to really understand your connections as well as your member sizes and so forth. So thinking about what's that connector plate is going to be put in the factory, how is it going to be loaded in the lorry, how is it then going to be held up and fixed on site? All of those things have caught me out in the past, and we've had issues with something along the way, and we've had to retrofit something at the end. And so really understanding those details before fabrication, during the design process, getting it costed correctly is super important. So yeah, it's just an example there of all the holes and the bolt holes and the screw holes that have to be pre-drilled will be done in the factory as well. So you really have to understand all of that beforehand. And then these are some pictures of some CLT that I saw being made. Lovely. Before it's been sanded back, you can see all the nice glue there hanging out the edges. But yeah, obviously we've got cross-laminated. Each layer is in a different direction here, as Wojciech just described, being pressed, being formed into the panels at once that they needed. And then this is an absolutely massive CNC machine that I saw. I think they told me it's one of the biggest going, so it's 50 meters long, I believe. And you could they put the CLT panels on here, and they actually have a kind of a tracking device that tells the machine at the end exactly where it is and what orientation it's in, and it will go along and cut exactly what it needs to less than a millimeter precision. So that is something you really have to think about as well, is the tolerances here, because everyone sort of always get told that you've got a 2 millimeter tolerance, but more often than not there's a 0 millimeter tolerance. And you have to remember that when you're designing things, you've got to think about how things are going to go together, because it's going to be exact. And particularly if you're thinking about refurbishments and existing buildings, and connecting into those, because they'll definitely not be exact. Or if you've got a hybrid project and you're looking at, say, a concrete core, which may have a 25 millimeter tolerance zone, and you want to connect some very precise beams into the side of them, or columns to the same height, then they're probably, you have to think about those connection details and ensure that the differences in between the two types of material are really captured at the beginning, because again, I've been caught out by that in the past. So just what do we do when we have a frame construction, a glulam frame with some CLT floors? What happens now? You've just seen now some images of the glulam beams being made in the factory. They're made with all their little notches and holes and steps, whatever they need, and the CLT in the same fashion. CNC cut, pilot hold, wrapped in protective coating, and then put onto the truck. And you've normally got a nice flatbed lorry. Flatbed lorry is probably about 13 meters long. So normally we try and keep your members to a 13 meter long maximum length. I think that also is the same length as a sort of shipping container if it has to go overseas as well. And so 13 meters is kind of like where you want to keep it, unless you've got to pay lots more for a special transport of some sort. But what happens is, the larger engineered timber manufacturers for sure have very sophisticated software that will also look at every single one of the members that you have in the delivery dimensionally, and create the perfect packing arrangement on the back of the truck, so it's as full as it can be. So you're using as little transportation carbon in getting your timber to site, but also they will all be stamped with a barcode and delivered just in time normally, and so they will all be very, very well controlled, and the person on site normally has some sort of scanner or iPad, and they know exactly what's coming, and they know exactly where it's going to land, and then which part of the building is going to go up first. So then actually the frame construction, those of you familiar with steel frame construction, it's not that much different. Your columns go up with a bit of propping, your beams go in, your floor goes in. It's very, very similar. The only thing I'd say is that the beams, it can all basically be done from cherry pickers very easily, because it's all very light, as long as you're not high in the air, that is. And there's some nice connection details that I've used on various projects now, where you have a hook on the top of your fin plate connector, which means you can balance the beam in without people the installers having to hold it in place whilst banging in the dowels or screwing it up or doing the bolts up. If you hook it on temporarily, then it's all in place. And I think I took a video of someone putting one of these beams in once, and it took about a minute and a half to put a beam in. So it can be very, very quick installation times. And then your CLT slabs go in floor by floor, and the CLT slabs that you can see. I've tried to draw some little laps here, so they'll have like a bit of a half lap between them, which means that then you just screw down nice and easily along the length of the panels, and everything's quite nicely tied together and creates a diaphragm. And then panelized construction, this is when we have mainly CLT walls, unless you have a big opening, which we've got some glue-lam framing out a big opening down here, but mainly where we have CLT walls and slabs. There are lots and lots of standard products for CLT to STLT construction. I'll show a few of them later, but they're excellent, they're super strong, and makes panelized construction extremely quick and easy to do with very minimal amounts of people on site. So here's some photos of one of our buildings, the boiler house, going up in such a way. I think there were only about 5 operatives on site to put this building up, and it was 6 stories. And yeah, it was very, very quick. And so I will now, I'm sorry, I just showed a snippet of later. I'll hand back to Wojciech to talk a little bit more about design.
Thank you, Kelly. I'm just going to share my screen again. Okay, and I'll remember to move this guy a little further up. Okay, so what I will try to do now is introduce you to structural design of engineered wood products, basically how things are calculated. I remember a few months ago when Tabitha reached out to ask me if I can deliver some slides on structural design on engineered wood products. I asked, how much time do I have? I would need at least 2 hours per product. It's like, no, can you do it in 20 minutes? It's like, okay, I can try. And this is my attempt to try to do it. The focus of next few slides will be really to point out the important aspects and some differences of structural design of solid timber versus engineered wood products. So bottom line, structural design follows the limit state design in a very similar way or same way as the design of solid timber members. When you've got the design load effect and design resistance, with design resistance expected to be higher than design load effect. I believe this has all been introduced to you in previous webinars. I'm not going to go into details, but I will just briefly mention about the design resistance and the modification factors, because this is actually quite important when talking about engineered wood products. So the design resistance is a product of a characteristic resistance of the particular product that's been modified by a modification factor and divided by the partial factors of safety. And you have an example of equation here. This design follows the Eurocode 5 principles. In terms of the characteristics of engineered wood products, the characteristic properties, what is important to remember, and this should not be new to you, that wood is an orthotropic material, which means it has different properties in different directions. And this is also true for engineered wood products. Okay, so this is very important to remember. So the orthotropicity of the product. The characteristic properties of engineered wood products used for the structure design can be obtained from either literature. For example, TDK have a vast library of resources that you can refer to, and I'm going to include the link in the following slides, I think, about how can you access the very useful literature. So this is, for example, characteristic properties of 2 types of LVL. So you have to be mindful about the actual products you're using, and then you refer back to the table of properties, and please keep an eye on the direction that your load is applied, whether it's a parallel or perpendicular to the grain, because the properties, the resistances will differ. Another source of information is the Manufacturer European Technical Assessment, or ETA, or Declaration of Performance. It sounds fancy, but this information is relatively easily accessible. It's in the manufacturer interest to make it as available as possible for designers. So you will find all information you will need for the design, for structure design in these documents, and they are usually freely available. So example here is the ETA of Storenzo's CLT. And last but not least is the source of information of characteristic properties of engineered wood products is the British or European standards. And as an example here on the bottom right, you have characteristic properties of glue-laminated timber, homogeneous version of glue-laminated timber. Again, keep an eye on the direction of the load that's been applied. So if you look at the symbols, you will find there that there is also always a number 90 or 0. 90 stands for perpendicular to the grain and 0 stands for parallel to the grain. And this is important to remember when designing. And then you see which direction your load is applied. Partial safety factors. I'm sure that you're not new to Eurocodes, particularly Eurocode 5, and you at least had a look at it. So you probably know already that the partial safety factors or modification factors may be different or are different for different wood products. For example, the recommended partial factor gamma M for material properties and resistances is usually 1.3. However, if you look at the second position there, it's glue-laminated timber is 1.25. So it favors slightly the engineered wood product, glue-laminated timber. So you're reducing the strength only by 25%. Rather than 30 like you would do for solid timber. I've added this note because that's quite important to remember that you should first of all look for this particular factor in the national annex to Eurocode. Also, the manufacturer European technical assessment will give recommendations of which factor to use. Strength modification factor. This is the factor that accounts for load duration and service class. So the load duration, humidity, and temperature in service. Again, this is the extract from the Eurocode. You see that the modification factor might differ for glue-laminated timber, LVL, plywood, and OSB. The table goes on. I had only so much space in this slide, but I think I send the message here that when you're designing with engineered wood products, you should refer to that and keep an eye on, so you're sure you're using the right number, the right modification factor for your calculations. In terms of the CLT, because CLT is currently not included in the Eurocode 5, but the rumor is that it will be. I think the latest update, the newest update of Eurocode 5 will come next year or the year after that. And the newer version will include CLT. For now, in most cases, at least as far as modification factor is concerned, it will follow the glue-laminated timber. Use the same K-mode as you would do for glulam. Another important modification factor should be kept in mind when designing engineered wood products is the size effect. So the characteristic strength may be increased by KH in the following circumstances. For example, in the glulam beams, where the sections are smaller than 600 millimeters and are subjected to bending and tension, you might increase by a minimum value of 1.3, or you use this equation here. Similar for LVL. So the rectangular LVL section other than 300 millimeter that is subjected to bending, again, you can increase the characteristic strength by 1.2, or the product of this equation to the right. And the last factor that is applicable for engineered wood products is the system factor that accounts for system effect when in the situation when load is shared between the structural members, for example, floor joists. But this is also applicable for the CLT, subjected to bending and tension. This is because there are boards parallel to each other, and those boards are often sharing the load. So the stronger board might be able to take additional load from the weaker board. And so if that makes sense. So the system factors could be applied in the design. Again, you should always refer to your manufacturer European technical assessment or design handbooks. The system factors usually between 0.9 or up to 1.2. That would depend on the boards that are subjected to tension. So again, this is as much time as I have. I have a few more slides, some interesting things to show you, but at this point, I would like to refer this literature to you. So this is all available on the Timber Development UK website. Some of them are actually available as we speak. Some of them will become available soon. Tabitha, later you can correct me if I'm wrong. I know I use these resources extensively. So if you are interested in learning more in detail about structure design of engineering wood product, please refer to this resources. This is a very, very useful source. Okay, so a little more focus now on mass timber, particularly glulam and CLT. Some general notes. Compared to solid timber, mass timber elements often have a greater average strength and less spread of strength values, which means it's consistent. I don't know, I haven't not attempted the previous webinars, but I guess there was a note about the grading and the characteristic values, the 5th percentile and so on, and the population. And so I'm not, sorry, I'm digressing here. The point being that the boards in CLT are right next to each other, and those boards will have slightly different properties. There'll be weaker boards and neighboring stronger boards, and the boards will be able to share the load. And because of the shared effect, the properties of the product is much more stable. So it's less spread between the strength, it's more predictable. And this is exactly what I just said. Weakest boards are distributed within the section, and the boards are often finger jointed, which means that the defects are cut off from the boards. Partial safety factors, as you've seen a few minutes ago, generally favor engineered wood products over solid timber because of this predictability. Strength and stiffness properties of CLT or glulam can be obtained either by determination and declaration of properties and geometrical data of the layers or the boards that the product is made out of, or by testing. Other relevant characteristics of mass timber systems include that they have relatively high strength in relation to the self-weight. Tight manufacturing tolerances means they have good dimensional stability. I believe Kelly mentioned that. And this has an impact on the, the effectiveness of the construction process. It can go faster, so there's less problems on site. And yeah, that opens up the possibilities for prefabrication of buildings. Okay, now a little more structure engineering. I will be talking to structure engineers or people interested in structural design. So I chose the CLT as my case study to show you some interesting things that should be considered when designing the CLT. When the panel is subjected to bending stresses, those bending stresses are generally carried by the boards that are running parallel to the grain of the layers, whilst the perpendicular or cross layers do not carry any bending stresses. This is not exactly true, but for the sake of design, we assume that's the case. So the cross layers are assumed as spacers. Bending stress distribution of the CLT subjected to the bending, the out-of-plane loading can be calculated using Binksy theory, very similar way as you would calculate bending stress for solid timber. However, the only difference is you would use what we call the effective flexural stiffness. And this effective flexural stiffness is calculated using only the layers that run parallel to the grain of the parallel to the main direction of the panel. So the symbol I stands for the number of the layers. So in this case, we have a 5-ply. You would only consider the first, third, and fifth of the layer to calculate your effective stiffness. And then once you do that, you calculate your maximum bending stress at the most extreme fiber, either the top or bottom. You then check the suitability of the section by comparing the design stress with the design strength of the board that's subjected to the stress. However, I might have neglected the cross layers a little bit, but they also have a very important function with the CLT. What I mean is they carry shear stresses. And because of the composite nature of CLT, shear stresses through the section are not parabolic as you would expect for normal rectangular section. They have the shape more like you see here. Then shear stress distribution of CLT subjected to out-of-plane bending can be calculated using this equation. It again looks a little scary, but it's actually not. It's very similar to shear stress calculations for solid sections. However, again, the difference of the first moment of stiffness and the effective stiffness of the panel. The first moment area of stiffness can be calculated using this equation. Again, considering only layers that you are interested in. I should also mention, or it's quite important actually, because as far as the shear design, it's the rolling shear that will often govern the design. And what is rolling shear? Is this kind of failure when the cross layers fail along the kind of growth rings of the boards. So yeah, so this is often the kind of property that dictates the design. So this should be checked. So you calculate your stress along the entire section, identify the location of the highest stress, and then you can compare that to the design rolling shear strength, which is usually around 1 Newton per millimeter squared. The exact values for each of the products are always included in the European Technical Assessment or Declaration of Performance. So those values will vary. That's why I should always refer to the ETAs. Last one on my today's slides is the in-plane behavior of the CLT. So obviously you're gonna have to sometimes design your element to withstand in-plane stresses due to compression or tension forces. So axial force is resisted almost entirely by the layers with the grain to the direction of the application of the load, force application, sorry. And this is the highlighted ones here. So when you're designing for compression, the equation is very similar. You should be familiar with this equation. For the stress or tension, sorry, that's compressive stress. The only difference is that instead of taking the entire cross-sectional area, you're only going to consider the layers that run parallel to the direction of the load. Same goes to designing for tension. Again, the net area is the area with the grain running parallel to the direction of the loading. And then you carry out the calculation, you identify your maximum stress, and then you compare it to the design tension strength of the boards that the CLT is consisting of. In-plane bending, bending behavior or in-plane bending behavior of CLT is analyzed considering only the parallel to span layers, very similar as it's been the case when I talked about compression and tension. Only the layers that run parallel to the direction of the load. So you carry out the calculations to identify the peak stress in the standard way, but again, instead of the normal segment of area, you calculate the net segment of area, considering only the thickness of the layers running parallel to the direction of the load. So yeah, we had quite a big ambitions about what to show you guys when talk about design of engineered wood products. It's like a lot up there that I was not able to cover, like in-plane shear analysis, mass timber connections, thin web joists or composite sections, or stress skin panels. There's quite sophisticated ways of designing these elements. Obviously, because of the limited time, I was not able to do it, but what I am able to do is refer you again to the literature. I can't recommend this enough. Please have a look if you want to learn more about structure design of engineered wood products. And the last section of today's presentation, challenges and barriers. Kelly. I'll stop sharing here. Oh, I can.
Okay, thank you. Hopefully this is going to come up in a second. Okay, so hopefully as well, perhaps we can have webinar series 2 with some of those topics covered, but we'll see. So I'm just going to circle back and just think about talk about some things that you have to think about in design, as well as sort of the production and the design for manufacture. But just something that parts of the structural analysis and parts of the detailing and the way you propose the building goes together that might be different from other types of materials, or a normal sort of REBA stage approach that structural engineers might take to design. So quite early on, we have to think a bit more about deflection than when we're designing a steel building, because timber creaks as well as just deflecting normally. And so you have to really look to try and limit large deflections, particularly cumulative deflections. So if you have secondary beams on primary beams with transfers, it's horrible. It's a nightmare. You end up with spreadsheet upon spreadsheet trying to figure out what's going to deflect when, at what part time during the construction and during the life of the building. And especially when you're looking at parts of the building that support things that are brittle or facades or glass, or and we have to limit deflections. We have to start thinking, maybe you're thinking more about deflection at kind of in stage 2 than you normally would with other materials. So that's one thing to think about. But also vibration. So we know timber's light. Its strength to weight ratio is incredible. It's great for adding to existing building. It's great for reducing your foundations, but it's also means it's gonna bounce a bit unless it's designed very carefully. So I've just got a little sketch down here of this was a part of a building we were looking at, sort of, well, it was actually in the US, and it's a architecture school, but the first floor slab is an auditorium, and it's going to be potentially in future subject to people moving in unison on it. And so vibration was a really big thing, and we had to look at this at kind of the scheme design stage to make sure our arrangement of elements was going to give us the a good enough natural frequency of the structure as a whole, and that analysis determined the size of the members. It was not the strength or the normal deflection criteria. So sometimes you have to think about vibration a little bit earlier in design than you might with other building types, and then also acoustics, because it's light, and perhaps you have to advise your clients or the architects or the rest of the design team that you need some acoustic engineer or specialist input earlier than you might normally in a design stage, because sometimes if the acoustic requirements are quite high, or if the acoustic engineer hasn't worked with timber and CLT and doesn't understand all the products that are available, they might end up asking for sort of very heavy wet trade finish, like thick screeds or heavy finishes that could potentially be looked at differently if you'd considered it earlier in the design as a team as a whole, or and then can like catch you out later when you've got quite far down the design process, and it's all of a sudden it's adding weight to the building. It increases your foundations, it increases your column sizes. And if you're adding to an existing building, it might mean that you have to strengthen it more or something. So thinking about acoustics early is really important as well. So three things there about kind of movement and vibration that you need to bring up and start having discussions about with the design team a lot earlier than other materials. And then also connections. I alluded to this earlier. I've got a few pictures here from Rotherblast connectors, but there are other suppliers out there as well. But just thinking about circularity, thinking about demountability. Also, we'll talk about this in a little while, but replacement as well. If areas of a timber building get damaged, how can they easily be replaced? So the connections are really, really important. And again, much earlier than normal. Maybe the type of connection you want to use to make your building easily demountable or easy to erect, or that might limit water damage during construction. maybe that type of connection could drive the way you design the building, the way you lay out the beams and columns, the way you and the architect work together to decide how the whole massing goes together. And so these things can influence the whole design process. And so thinking about them at the start again is super important. And here's an example of that same building I showed a moment ago, but we were thinking about the connections of this at the very beginning. These are some initial sketches of how it all might go together to limit how much steel we would have in there. Like before we even won the job, this was for the competition, and then that developed through scheme and detailed design into really understanding how those elements would rest against each other. What was in just pure bearing, what needed some tensile capacity, what needed ductility, where we needed to add steel to its most effectiveness. And again, that really led the geometry of the whole sort of truss in this case, but also then that led on to the geometry of the roof, and then that led on to the different buildings. So we worked through that as a design team to get the right solution. And then you have to really think as well, particularly when you're looking at sort of larger scale buildings rather than houses as well. But if you're looking at offices or larger residential buildings, you have to think about where your mechanical and electrical service routes are going. Probably again a bit earlier, we can't just put a whole load of cellular beams in, and we don't have a nice flat slab like you would with concrete, and so you can't think about how the services route through later. You have to think about that at the start, because your beams are going to be deeper. You can only put small holes through them because otherwise the timber can split. But if you're clever about it, you can really arrange your structure in a very coherent way with the M&E and the larger ducts and smaller ducts, and wherever your sprinkler pipes need to go, or if it's going to be in the floor, or if it's going to be on the ceiling. All those conversations need to happen at the beginning so that you get the arrangement of the column grid correct, you get the positioning of the risers in the core correct, and you can really maximize on getting a good span of your CLT, and then fire protecting where it needs fire protecting, exposing where you can, and all those things. It's all tied together. So let's talk a little bit about durability, because it's an issue. Timber gets wet and it rots. It's a fact. We know it. We've seen it. CLT in particular is a super material. So actually, when something like this is an image from a cross report a couple of years ago, when it gets wet on the top and rots, you can't even see it at the bottom because it's so good that it doesn't soak through, and you can't see it like you would with plywood or a joisted roof. And so we have to stop this happening. Just let's also say, if this was the concrete slab, the cover would have gone on, the rebar would have blown as well. It's not just a timber issue. This is the workmanship of the waterproofing issue. But the thing is, we can't see it, and we need to make sure that we're not losing our structural strength if something happens. And so we need to think about how we detail this. We need to have falls on a roof, really. No other way around it. Put some falls in, put some detection in. There are amazing detectors out there now you can put in very easily. Speak to a BMS, speak to the building management system, and tell you if the moisture content's getting too high. You can the architect needs to think about how they're layering up the waterproofing. Where is the point of failure if it's going to happen? Are there 2.2 layers of protection? Is it sort of embedded in the timber, or is it on top of the timber? Think about the routes the water can go and where it can drain away to. So all needs thinking about from the very start. And then also site control. So some lovely photos here of a nice wet site. So the first off, I mean, your floors, as long as they're taped up, it's actually quite difficult unless you've got water sitting there for months on end to penetrate through the top of the CLT slab. The risk areas are at the joints, and so the joints all need taping, and you can see that they're all taped up on here. and the edges where you've got the end grain. So you can see from this photo at the top that the grain is going through each lamella. That grain is a capillary basically that takes water through a tree. And so as soon as it sees water, it starts sucking it up. And so you don't want it to get in the end grain, basically. You need an edge protection. There are edge protection products out there, and your CLT panel should come with it, but you need to make sure it's in your specification. But, you know, temporarily, if it rains, there's a bit of water like we can see on this photo, bottom left on site, provided you've got the correct people on site looking at that, making sure it's open to the elements so wind can come through, dry it out. Also, they brush off, they scoop up, they de-water as they go. We need to make sure that that doesn't sit there for months on end, basically, because if that happens, then you get something like the top. But as long as it's sealed up, it's okay for a few months. And then once the cladding's up and everything's watertight, everything will be moisture, have moisture sensor tests to make sure it's at the right moisture content, and then the building can be starting to be used. Now I've got a picture here of actually where you also need to really think about those connections, like I mentioned earlier, because on site, if it's exposed to water and there's a nice spot where water can get in and sit and leak through, and if it gets stuck inside a steel plate and then it's in your connection and you're rotting all of the wood around your dowels or bolts or screws, then that connection is going to lose its strength extremely quickly. So you need to make sure that your connections are really well detailed, really well thought through, and on your site inspections, if you see something like this, make sure there's extra measures in place that has that has then been tested with a moisture sensor afterwards to make sure hoovered out. You can get little vacuums in there to get the water out afterwards, tested, and then plugged up and sealed so that it can't get back in there later. And everything from the top should be a little bit more sealed up so the water can't get in there in future. So there's little things like that I mean, it will be part of a water management plan from the subcontractor, which you should always ask to see before they start on site. Which is very common now. The major subcontractors in the UK do that as standard, but if you've got a smaller outfit doing, or someone doing, main contractor doing it for the first time and they're not aware of it, and you need to make sure you're asking for that as the engineers as part of the site phase of works. But yeah, as long as that's all in place and the building can breathe, then you can get around the site phase. And then there's fire. I mean, this is at least 10 webinars on its own. So in a similar way to Wojciech, I'm not going to go into the fire engineering today or the detail of how we do fire design. But there are lots of resources out there to learn about fire and CLT and how it's different from solid timber to engineered timber and laminated timber. Where perhaps the different lamellas and the different glues can have a different effect on the fire performance. And so this is the website you can go get to, a link from Timber Development UK. We can also just Google it. That's really useful and can give you either a technical level 1 or a technical level 2 explanation, depending on how technical you want to get on how fire safety design works for timber. And there's also some excellent risk-based guidance out there from the Structural Timber Association by OFR and a consortium of other participants as well. Various industry suppliers, subcontractors have all come together to do this, and it sort of looks at the risk in a similar way to disproportionate collapse. As you look at your overall height, what are the uses, what are high risk, what are low risk, and then what's your best route to compliance in terms of approach to fire engineering. So this you need to think about early on, and if your fire engineer on the project has not worked with mass timber or timber before, then you need to have a really good conversation about that really early, and give them all the information they can that they need as well, because it's really with timber, it's not just the fire engineer working in a silo, and it's not just the structural engineer working in a silo. We have to work together to come up with the design. And then also there's insurance. I'm sure everyone's heard about this, but we have, we've had a few struggles understanding the insurance industry and the insurance industry understanding us. And so there's now a great book out there called the Mass Timber Insurance Playbook. You can download for free from the ASBP website. There's also a really useful white paper by the RSC authority, and it really talks you through, because basically I've been to a lot of events now with insurers, and I know way more about insurance than I thought I ever would. And what it seems to boil down to me is just talking the same language. Like we're basically doing what they expect and what they want, but we're not explaining it in a way or at the design stage that they want to hear it at. That means that they understand the risk profile and they can give a proper advice on what premium might be, or if there's any extra or not. And so reading through these documents as part of and engaging with the insurance brokers and the client's insurer early on in the design process can sort of get through all of those barriers, and you start to see a way through. So I would recommend having a look at that literature as well. And here, this is kind of the sort of latest advice: is get your insurance broker on stage 2. If you can find a fire engineer that's experienced in timber, make sure they're part of the team. You know, a subcontractor that has built before, an experienced one, bring them on a PCSA early in the design period, because they're probably doing some testing on another project right now that helps inform your design, or they've probably just come across something that the fire brigade or the approved inspector wants to see that you might not be aware of, and so their literal week by week knowledge on this is invaluable. And then also, you know, with the new Building Safety Act coming out, etc., there'll probably be more golden thread principles. But I mean, it's been quite the approach on timber buildings for quite a while now. You have a peer review, and you involve specialists and fire and advisors to sort of review things as well. So you know, all those sort of golden thread principles should run through the project. And that is everything I had to share. Thank you.
Well, thank you both, and thank you for Wojciech for answering the questions in the chat in the screen. We have run over time. I know there was a huge amount to you know, get through, and so important, and so didn't want to cut you off. So where answers to the questions haven't been put in the chat, we will just come back to you individually, having answered, you know, the ones that haven't been answered, and email you with those. But with that, I'd just like to say a huge thank you, Kelly and Wojciech, for giving your time, for your experience, and educating all of us, but also our current and future engineers. Now it won't move along. Let me move it. So, as I said, engineering resources, thank you for all the shout outs. The links have been put in the chat, and they will come out again in the following emails. We also run a student challenge, so if you're an engineering student watching this, come and watch out for TD Challenge 24, all about houses and homes. And next week, we carry on with our 6th webinar, Detailing with Timber, where we'll hear from Beth Williams and Toby McLean. So with that, I'd like to say a huge thank you to all for joining us.